This is Geometry Unit 8, Lesson 7 on perimeters, areas, and volumes of similar figures. So what we're going to look at are some comparisons that we have between perimeter, area, and volume and the ratio of the sides. So let's review first of all what the measurements of perimeter, area, and volumes involve. When you do perimeter, lengths are measured in units. So whenever you measure something, you're just doing a certain unit. It could be inches, it could be in feet, it could be in centimeters. We don't know. So if you're doing the perimeter of something, you're just measuring a bunch of lengths and adding them together. And they would be in one of these units, for example. All right. However, if you're doing the area, remember you have to multiply something, length times width, to figure out area most of the time. So because you're looking at a two-dimensional figure. That means area is measured in square units. So if you do inches times inches, you get inches squared. Feet times feet would be feet squared. And centimeters times centimeters would be centimeters squared. So area is in square units. Now volume is 3 dimensions. If you're filling something up, you're doing its volume. You have its length, you have its width, and you have its height in general terms. So that means you are multiplying the units 3 times. So volumes are actually measured in cubic units. So you would have cubic inches, cubic feet, or cubic centimeters, or any other unit that you may happen to have. So that's an important clarification when you're doing the units, why the units are what they are. So that brings us to some interesting things for the kind of ratios that we have for similar figures. If two figures are similar, all pairs of corresponding segments are in the same ratio. Now remember, segments would be lengths. Okay, so that means the units are going to be the same. So if it's perimeter, it's going to be all the same units. If you have a side, that's a length. Medians are a length. Altitudes, angle bisectors, diagonals, and perimeters. If you know one side ratio, you actually know the ratio of the sides, you know the ratio of the medians, you know the ratio of the altitudes, you know the ratio of the angle bisectors, you know the ratio of the diagonals, and you know the ratio of the perimeters. It's always going to be the same because you're just comparing the lengths. Okay, now, the ratio of the areas is actually the square of the ratio of the sides. Remember we said the sides would be the lengths. To get area, you have to square something. So if the ratio of the sides is 2 to 3, we automatically know that the ratio of the areas will be the square of this. It will be 2 squared to 3 squared, which is equal to 4 to 9. So if you know the ratio of the sides is 2 to 3, the ratio of the area is 4 to 9. All right, what if you know the ratio of the areas is 25 to 36? What would be the ratio of the sides? Well, what was squared to give you 25? Well, that's 5 squared, and 6 squared is 36. So the ratio of the sides would be 5 to 6. So if you know the ratio of the areas, just take the square root, and you've got the ratio of the sides. And the ratio of the volumes, remember volume, you had to multiply length, width, and height, and cube the units. The ratio of the volumes is the cube of the ratio of the sides. So if you know the ratio of the sides is 2 to 3, the ratio of the volume will be 2 cubed to 3 cubed. 2 cubed is 8, and 3 cubed is 27. So the ratio of the sides is 2 to 3. We cube them to get the ratio of the volumes. If you know the ratio of the sides, just cube it. And if the ratio of the values is 1 to 64, then the ratio of the sides is, well, we'd have to take the cube root. 1 cubed is equal to 1, and 4 cubed is equal to 64. So this is actually going to be a ratio of 1 to 4. So if you know the ratio of the sides, you can square it to get the ratio of the volume, or ratio of the area. If you know the ratio of the sides, you can cube it to get the ratio of the volumes. And if you have the ratio of the sides, it's also the ratio of anything that you would measure just the length on. Okay, so let's try a couple of problems that deal with this. Okay, the lengths of the longest sides of two similar quadrilaterals are 8 and 12. All right, this is a similarity problem, which means immediately I'm going to draw myself a picture. Now, a quadrilateral is any 4-sided figure, so I'm just going to draw a random 4-sided figure like this. I don't know what it's going to look like. It's going to be something like this. And then I'm going to draw a similar one. It's a little bit bigger. So it's similar, but not congruent. One's bigger than the other. Okay, and it says, the lengths of the longest sides of two similar quadrilaterals are 8 and 12. So this is the smaller one, this is the larger one. So this looks like my longest side is going to be 8. This one's going to be 12. All right, it says the diagonal of the smaller quadrilateral is 10. Here's the diagonal. And that's going to be 10. And I'm going to draw the same diagonal in the other other quadrilateral, excuse me, but I don't know what it is. So I want to figure out what that diagonal is going to be. All right, so what we need to know is what the ratio of the sides are. Now these are similar quadrilaterals, so the ratio of the sides, or the ratio of similitude, is 8 to 12. You can reduce that if you want to. 8 over 12 reduces to 2 over 3, so you can simplify if you want to, or you can leave it 8 to 12, doesn't matter. Okay, so the ratio of the sides is going to be 2 to 3. Now, diagonals are length. Is any of the units going to change if we're just measuring the length? No, the ratio of the sides is going to be 2 to 3, so that means the ratio of the diagonals will also be 2 to 3. Will also be in a ratio 2 to 3. So when you set up your ratio, 2 is to 3, or 8 is to 12, it doesn't matter, you've set up the ratio the same way. 8, 12, or 2 to 3, is as 10 is to x. Make sure they're in the same units. Smaller to larger, smaller to larger. Cross multiply, you get 2x is equal to 30, divide by 2, and x is 15. So that means that your diagonal here will be 15, because you're just using the ratio of the sides. Now, if the area of the smaller quadrilateral is 60, find the area of the larger quadrilateral. This is where knowing the ratios comes in handy. All right, we don't know what the area of this figure would be. There's no really formula for this kind of figure. Well, there is, but we don't know enough information about the rest of it to do it. However, we don't know that the ratio of the areas is equal to the ratio of the side squared. Because remember, area is squared, so you take the sides and square it, and you get the area. Okay, so if I want to figure out the ratio of the area, we figured out the ratio of the sides back here was 2 to 3. And if I square that, that will give me 4 to 9. So the ratio of the area is 4 to 9. All right, so now if I want to compare the smaller quadrilateral is 60, the area, smaller to larger, 60, to the larger, we don't know. 4x is equal to 540, and then divide by 4, and x is equal to 135. So that means the area of the figure is going to be 135. And we did that without having to know any area formula at all. We just had to know that the ratio of the sides squared is the ratio of the area. So there we go. Joe A. Guy is 6 feet tall. He weighs 175 pounds, and the total volume of his body is 2.8 cubic feet. In a science experiment gone horribly wrong, Joe manages to enlarge himself by a factor of 8. He is now 48 feet tall. So that means that he increased by a factor of 8. He multiplied by 8. So the ratio of his size, or his length, he went from 6 feet to 48 feet. So that is a ratio of 1 to 8. That's his ratio of his size is 1 to 8. So how tall he is a ratio of 1 to 8. Now, that's just a length. You would just pull out your yardstick and measure 1 to 8 for his feet, or a ruler, whatever you happen to have. Now, it says, what's his new volume? Well, how does volume compare to just length units? The ratio of the volume is going to be the ratio of the length cubed. So the ratio of the volume is going to be 1 to 8 cubed, and that's going to be 1 to 512. So his volume started out, whatever he has, is going to be a multiple of 512. So if we set up the ratio 1 to 512, what was his original body volume? Was 2.8 cubic feet. What's his new volume? We don't know. Old to new, old to new. Cross multiply. 512 times 2.8 is 1433. 0.6 cubic feet, or feet cubed. So we just figured out what his new volume is when he increased his size by a factor of 8. It's going to cube what his volume was. All right, now what about his weight? Well, his weight is proportional to its volume. So whatever you weigh is proportional to its volume. Proportional to volume. The more you weigh, the more your volume is going to be. So we know we're going to have to use the cubic of the volume again, which was 1 over 512, and compare what his weight was. Well, his weight, he was 175 pounds. What does he weigh now? Well, we don't know. Cross multiply, 512 times 175, he actually weighs 89,600 pounds. That's how much he's going to weigh now when he increases his volume by a factor of 8. Okay, so what you have to remember, perimeter and any other length has just the same ratio of the sides. Area is the ratio of the sides squared, and we'll have square units. And volume is the ratio of the sides cubed, and we'll have cubic units.